In section 1.3 we're going to be looking at several different graphs of functions and lots of new or what might be new vocabulary. You can pause the video and copy down some of this important vocabulary. I'm going to continue starting at section 1 with more explanatory type information. So we're going to be looking at the graphs of functions, something called a greatest integer function. When you graph it, it creates a step function. And what is an even and an odd function, and how can you tell the difference? So let's talk about the use of open and closed circles in our graphs. If we use an open or closed dot at the extreme left and right points of a graph, then that would indicate that it doesn't extend beyond those points. So if you have a closed dot, that indicates that the value is within the domain. Of the function. If you have an open dot or circle, then the value is not included in the domain. Sometimes if I have a closed dot, I'll say that that is inclusive, and an open dot says that whatever the value is exclusive or excluded from the domain. So we're talking a lot about domain. How do you find the domain of a function from its graph? You can just look at the x values. That are included in the graph or the function. And to find the range, you look at y values. So you definitely, when you have a graph, you need to look at if there are circles or open or closed circles, or if there are arrows. If there are arrows, that function goes on to infinity, and so generally you would have a domain of all reals when you see something like this. For that same graph, if I were looking for the range, I have to notice at what y value is that function defined. So there are no y values less than 0 here, so the range of that function would start at 0. And then since there are arrows, it would go on to infinity. The vertical line test is something you should be very familiar with. So I'm going to write the actual full math definition. A set of points in a coordinate plane is the graph of y as a function. If and only if, as a function of x, if and only if no vertical line intersects the graph at more than one point. So that is the official definition. Let's practice using that definition with some examples. So we want to determine in example 1 whether or not each graph represents y as a function. And so this is where you can use the vertical line test I actually like to think of it as the pencil test. So I don't have a pencil handy here, but I have a marker. And so if I take my pencil or marker and I move it across in a vertical line, if my pencil touches the function at more than one place, then it's not a function. So I can roll my marker across in function A and never touch in more than one place. So therefore A is a function. So we'd say yes. And then for choice B, if I'm going across with my marker, I can see very quickly that at many points I'm touching the graph of the function in more than one place. So therefore choice B is not a function. So some other terminology: a function is increasing on an interval if for any x1 and x2 in the interval x1 is less than x2 implies f of x1 is less than f of x2. A function is decreasing when we have the inverse of that true. And a function is constant on an interval if for any x1 and x2 in the interval f of x1 is equal to f of x2. So as we look at different graphs, we'll determine intervals on which functions are increasing, decreasing, or constant. Okay, so in order to show increasing and decreasing, I'm going to draw an example graph. So here's my x, here's my y-axis, and say I've got, here's y equals 1, I've got a function we'll say that's a parabola that intersects with a line. This might be like a piecewise function. And let me sketch in some values here on my x-axis. 1, 2, 3, 4. And instead of arrows there, let me put some closed. I'll close that off. And so just to show where I'm intersecting, so this is right on the axis. Here we are at 2, and here we are at 4. Okay, so to find an interval on which the function is increasing, I would call this x1 and this x2. So where x1 is less than x2, f of x1 must be less than f of x2. So by visual inspection, you can say, well, as I'm going from left to right, on this interval starting at 2 and ending at 4, my function is increasing. So the way I would write that is it's rising from x equals 2 to on the interval from 2 to 4. Then to find an interval on which the function is decreasing, so now I'll call this x1 and this x2. So visually you can see my function is going down in that interval. But according to my definition, x1 is less than x2, but yet f of x1 is greater than f of x2. So visually you can see that the equation matches. So I would say from on the interval -2 to 0, that's when the function is decreasing. And then to find where the function is constant, so now I'll call this point right here point A and point B. I'll let A be point x1 and B be point x2. So at x1 and x2, f of x1 is equal to f of x2, and so that interval is from 0 to 2. And that's where f of x1 is equal to f of x2. Here f of x1 was greater than f of x2. Here f of x1 was less than f of x2. The next sort of terminology we need to be concerned with are our relative maximum and minimum values. A function value is called a relative minimum if when there exists an interval x1, x2, that contains A such that x1 is less than x is less than x2, so that f of A is less than or equal to f of. Okay, so I really dislike those very mathy definitions, but I feel they are important for building your foundation towards calculus. So let's go ahead and define our relative maximum of f if when there exists an interval x1, x2 that contains A such that so there's some value of x between those two where f of A is less than or equal to f of x. Okay, my preferred definition, so the point at which a function changes from increasing to decreasing, that is going to be your so let's see, we were increasing and now we're decreasing, so visually you can see that is a relative maximum. And then the point at which a function changes from decreasing to increasing, well, that's a relative minimum. So you can see it's the lowest point on the graph or the highest point on the graph. To approximate the relative minimum or maximum function using a graphing utility, so you've got a max or min. Once you graph something, you have a max and min function, and we'll work on how to use that. So a lot of these things come in, we don't just use them when we're graphing parabolas. We're going to be looking at some functions that are really, you know, sixth order functions. So we've got a relative minimum right here, a maximum here, another minimum here. But you can see this isn't the highest point ever in the graph. The highest point is infinity in the entire function. But we're just looking at our, we're setting these different little ranges, and we want to see in between those ranges, are there high points and low points? So for our example here, we'll take a look. Oh, let's see. My little doggy wants to say hello. She's She's sitting right by my lap while I'm filming here. That's Zoe. Oh, now she goes and lays down. All she wanted was a little bit of attention. She wants to be a movie star. Okay, so in example 2, we've got a function c representing the annual number of cases in millions of chickenpox reported for the year X in the United States from 1960 through 2000. Interpret the meaning of the function's minimum at 1998, 3. So let's see if we can find a better picture of the full graph here. Okay, so it appears that I don't have a picture of this graph. I don't have any information other than what's given right here. So when it says interpret the meaning of the function's minimum at 1998.3, so I can construct, I don't even have to know what the graph looks like, but between 1960 and 2000, so that graph is doing something, but we know just a snapshot at 1998, that graph has a point at 1998, 3. So, and they're telling us that that is a minimum. So that tells me that it was higher over here, and it's going to be higher over here as well. So there were 3 cases in 1998, and that was the lowest number, well, not 3 cases, 3 million cases of chickenpox, and that was the lowest number at any point on this graph. So that's really the point of that question. Next, we're going to be looking at the greatest integer function. You can follow along on page 34 in your book. There's a picture of a piecewise function and the greatest integer function. And so if we're going to describe that graph, we are going to see that it looks like it's a step function. And so here's 1, 2, 3, -1, -2, -3, -1. Okay, so starting at 0, we have an open circle at 1, and then we jump up, and at 1 we have a closed circle. So the meaning of this step function is that, say I have a number 2.1. The greatest integer that 2.1 can be equal to is 2, and that's true for any of those rational numbers between 2 and 3. The greatest integer is 2, and then once we get to 3.0, that's when we jump up to 3, and all the decimals between 3 and 4, the greatest integer value that it can be equal to is 3. So let f of x equal the greatest integer function of x. Find f of 3.74. So all the decimals between 3 and 4, the greatest integer is going to be 3. To sketch the graph of a piecewise defined function, we kind of already talked about that in our piecewise lesson. We want to sort of isolate the domains and graph the individual functions. Okay, and the last important definition in this section is going to be your even and odd functions. A graph is symmetric with respect to the y-axis if, whenever x, y is on the graph, then negative xy is also on the graph. So let's draw a visual example of an even function, and that would be y equals x squared. So that's a parabola. That's the parent function. So if I've got, say, 1, 1 is on my graph, well, then the symmetry would have to be negative 1, 1 would also have to be contained on my graph. A graph is symmetric with respect to the x-axis if whenever xy is on the graph, x negative y is also on the graph. A graph is symmetric with respect to the origin if whenever xy is on the graph, negative x negative y is also on the graph. A graph that's symmetric with respect to the x-axis is not a function. And just hearing those words, symmetric to the x-axis, if you can't visualize that, what you want to picture is something that is the same on both sides of the x-axis, and you can kind of see right away that anything that's symmetric to the x-axis is going to fail the vertical line test. So those won't ever be functions. But we are very interested in if things are symmetric to the y-axis, then we call that an even function. We can tell by looking at the graph, or we can tell by substituting f of negative x, and we would get the same value as we get for f of x. A function is even if for each x in the domain of x of f okay, I think that's a typo. So this one we want to say a function is odd. F of negative x is equal to negative f of x. There we go. Okay, so I would like to go through example 10 for even and odd functions, because those are more like the types of problems you're going to be working. So I've got 3 functions here. A is g of x, and that's going to be x cubed minus x. B is h of x, and that's x squared plus 1. And C is f of x, which is x cubed minus 1. And say this were on the no calculator section of your exam, and I want to know if each function is even, odd, or neither. So the technique that you're going to use is you're going to take and you're going to substitute negative x into the function. So let's do negative x cubed minus negative x, and we're going to see what we get. So negative x cubed is, well, negative to the third power is negative 1, so that's going to be negative x cubed. And then minus minus x, that's going to be plus x. So we need to analyze, is this the opposite of g? Because to tell if it's odd, we have to say g of negative x equals negative g of x. Okay, so negative g of x would just be having everything be the opposite, and that is what happens there. So we could say that function a is an odd function. To look at h of x, I'm going to plug in h of negative x. I'm going to substitute it, negative x squared plus 1, and when I do all my algebra and simplify everything, I get negative x squared is just the same, x squared, and then plus 1 doesn't really change. So here I get h of negative x, it's equal to the original, and so when that happens, that's when we have an even function. And so just the way textbooks work, I'm going to predict that C is going to be neither, but let's go ahead and prove it out. So for C, I want to do f of negative x. So I'm going to substitute negative x cubed minus 1. So negative x cubed is just negative x to the third. The minus 1 doesn't change. So if I inspect my original function, x cubed minus 1, negative of that would be negative here and positive there, so that didn't happen. It's not the same because I have this additional negative introduced. So when that happens, that means it's neither even nor odd.